So hi, welcome to day two of distance learning. So here we go. Today we're looking at energy utilization. So we've got storage and distribution of energy. So this is the technical term or the technical definition. So it's a method with which energy is used, right? So utilization always means how you're using something. So in other words, how do we produce energy? Really, we're talking about electricity, how much is used to produce materials and products, okay? And then also the effects of this. So we're going to be talking about, for instance, the carbon footprint of products, and this kind of goes with the whole idea of waste mitigation from the last section, in the sense that if you reduce and dematerialize some of the waste, then you're going to also reduce the pollution, especially carbon dioxide that's causing climate change. Okay, so by the way, these are some of the methods for generating electricity. You've got these renewable ones like wind and solar. This is hydroelectric, which is also renewable. And then we've got our sort of non-renewable guys here down here. This is probably coal-fired. In fact, you can see the pile of coal right down here. And these are called cooling towers. And so they would be with nuclear or coal or natural gas powered. And that's really the steam that's coming out of the turbine, um, that's helping to cool them down. Okay, so here we go. We're moving on. All right, the total energy required to produce a product. That's what we call embodied energy. And this is really this idea from cradle to grave. And you just kind of have to think through the entire life cycle. So we're talking extraction, transport, making the product, transportation to the site, construction, um, maintenance, demolishing, transport of waste, all the way back to till its grave. And this could go for any product, right? In this case, they're talking about buildings, but it could be for anything. And we've sort of hit on this with an aluminum can. It would be extracting the bauxite that you need, transport to the smelting factory, smelting the aluminum, transport to the site where you would actually make the aluminum can, transports from there to the site where you fill the aluminum can with Coke or whatever, transport to the store where you would actually store that, or probably even in between that, you'd have a warehouse that it would go to. Then it would go to the store, and then transport from the store to the consumer's home, where you would, conceivably do things like put the Coke in a fridge to cool it, and then transport, once you've drank that, the transport of the waste back to the landfill or recycling. Okay, so there's a huge amount of energy. These up here represent the carbon emissions, and here down here is sort of the embodied energy. So when we're talking embodied energy, we want to also think about embodied carbon, which we'll get to. This video is pretty good about what embodied energy is, so you should pause and have a watch of that. Okay, we're back. So embodied energy, what we're going to be talking about is how do we measure it? So we're going to be measuring this in something called megajoules per kilogram of material. And I always think in science, and when we are a science, it is so important for you to understand the units that you're using, right? So a joule, which we use a J as a short form for, is a measure of energy. And it equals, well, 1 joule is equal to a Newton meter. So it's the amount of energy required to apply a force of 1 Newton through 1 meter. So you can think of this as roughly the amount of energy it takes to lift an apple from the floor to a height of 1 meter. Okay, an apple is about a Newton. A Newton roughly correlates to the amount of force it takes to lift 100 grams in our gravitational field, so Earth's gravitational field. Okay, of course that's going to be different. A Newton, will get you farther on the moon because there's less gravity. But here on Earth, it's roughly lifting 100 grams, 1 meter. Okay, you can also think of it as this. This is another way that the joule is defined, and this is actually probably more useful when we're talking about electricity. Uh, it's the amount of energy expended using 1 watt of electricity for 1 second. So if you think of those little LED lights that we have, the small ones that you might have used in the which unit was that? In the control freak unit in grade 9 where you built like Arduino stuff, those are 3 watts, right? So, basically them running for 1 second requires 3 joules of energy. Okay? Now, a megajoule is 1,000,000 joules of energy. So, it would be it would be the amount of if you had a megajoule of energy, it would be the amount of energy required to lift an apple, 1,000,000 meters or 1,000 kilometers. Okay. Now, of course, it's not as simple as that because you trying to lift an apple 1,000 kilometers straight up into the air would take quite a bit more energy because of lots of reasons. You know, but we won't get into those right now. But anyways, that's what the equivalence is. So mega means million. Okay, another one that we measure in it has to do with CO2. So the unit is kilogram CO2 per kilogram. So this is kilograms of carbon dioxide per kilograms of material. So for instance, to produce 1 kilogram of aluminum, 8.24 kilograms of carbon dioxide is produced to make 1 kilogram of aluminum. So the aluminum, 1 kilogram of aluminum would be this kilogram right here, the one on the right. Kilograms of CO2 would be on the left. Okay, and this is a division problem, honestly and truly. These are division problems, right? Kilogram of CO2 per kilogram. This kilogram of material would be on the bottom of this kilogram CO2. Okay? All right. Now, you're going to need to be able to do some simple calculations based on this, and I would expect that you would be able to set these up correctly. So, there's a chart in your text, and it looks basically like this, and it's showing the energy right here. So the energy in megajoules per kilogram. So aluminum is 155, etc. Right? And then this is your carbon emissions for that. Okay, so how much energy is required to produce 18 kilograms of copper? Well, you would take this right here, which is 42 megajoules per kilogram, and you set it up as a fraction, 42 megajoules per kilogram, and then I'm multiplying it times 18 kilograms, right? Now, I want to know energy kicking out of this, so this kilogram right here and this kilogram right here, these units cancel each other. So that leaves me with only megajoules. And then it's really just a multiplication problem of 42 times 18, and that's going to give me 756 megajoules. Okay, now we're going to get into energy distribution. So once we know we need energy to do things, so how do we get it places? So, it starts off with generating power. And what I would like you to do is actually watch this video. I do apologize, he does have some commercials in it, but you can skip those or ignore them. But it's really actually quite a good video. It shows you how power is generated. Okay, and we talked a little bit about that when I showed you the first slide for topic 2.3. But watch this video, he gives you some more insight on actually how it happens. Okay, so I'll stop for a second. You can pause me, go watch that video, and come back. Okay, same guy. He talks about the power grid. So the power grid is basically where how most sort of developed countries around the world get their power from one place to another. Okay, and so he's going to explain what that is. So go ahead and pause me, watch this video, and enjoy. Okay, here we go. Now, what we're going to do is talk about something that the IB wants you to do. I'm sorry about the spelling error. I'll fix that later. But the combined power and heat. Okay, those are known as CHP. Right, and so these plants generate heat and power for local communities. Okay, basically a lot of, and you can see this in the text, a lot of energy is wasted in the form of heat. In fact, if you remember when I was talking about those cooling towers at the beginning, there's a lot of heat that's lost in those. But if you can capture that heat, you can make the generation of power more efficient. So this is actually, GE makes a combined power and heat plant for more local communities. So this would be something that you would want when you don't want to have like a huge grid. Okay, so this could power more local type things, more local areas rather than whole parts of countries. Okay, again, this is another thing about local power generation. So you want to watch this video. It's going to describe how there's right around the world, rather than having these big power plants, people are starting to do more local power generation. Okay, so that's generating power at the local level that feeds into the grid. Okay, so have a go at watching this, and if you remember back to the video that was back here about the grid, he talks about the um, more people and plants and things like that are attached to the grid, the less disruption to services. So the same thing happens here. The more local power generation that goes on, the less disruption to service. Okay, let's talk about a quick case study in fuel and in energy. So let's compare a gas-powered car to an electric-powered car, right? And let's look at some of the advantages and disadvantages of those. So, when we look at a petrol or a gas-powered car, one of the biggest advantages, and probably its greatest advantage right now, is it has a greater infrastructure. In other words, there are gas stations or petrol stations all over the place. So if you run out of petrol or gas, you can go fill up and be on your merry way, right? That's a big disadvantage of electric cars, is that there's just really not a great place for charging them right now. If you wanted to go long distances, if you were planning to drive through the empty quarter, you would have a hard time in an electric vehicle, whereas there's infrastructure to support petrol and gas powered vehicles. Okay, so that's one of the biggest advantages of gas and one of the biggest disadvantages of electric. Now, this is changing. There are more and more infrastructure being built for electrical powered vehicles. Electric powered vehicles are great for local travel because you can plug them in at your house. If you're not going long distances, they're much better. Okay, now when we talk about these two, when we talk about large embodied energy, remember that embodied energy is from cradle to grave. So you'll see a lot of videos out there that talk about the fact that it takes more energy to create an electric vehicle than it does to make a petrol powered vehicle. However, over the lifetime of that vehicle, the embodied energy is smaller. So from cradle to grave, you're using less energy to run an electric vehicle than you are to run a gas-powered vehicle. Okay, great advantage for petrol powered. They're cheap. They're much cheaper. You can buy a car for, I don't know. You can buy a brand new car like a cheap, Tata or something like that for a few $1,000s. Whereas getting a cheap electric car, probably not as easy. Okay. In fact, here at Kaus, those golf carts, those electric golf carts, to buy one, not to lease one, but to buy one almost costs, well, it costs as much as buying a petrol car. Okay. Now, this is the thing that could change, and this is a disadvantage of petrol-powered cars, is it is definitely infrastructure dependent. You can charge your car with solar, so you could get the electricity you needed from solar. But you need a petrol station if you're not going to go and dig up oil from the ground, process it and refine it so you can't run your own petrol-powered car. um, you need infrastructure, whereas you could charge your own electric vehicle. So that makes that quite an advantage. Um, a great advantage of a petrol powered car, they're super, super quick to fill, right? Like you just go to the local filling station, boom, you're done. Okay, slow to charge, although this is changing, but electric vehicles take much longer to charge up. The maintenance on electric vehicles are much, much cheaper. There's just so many less moving parts and things that need to be maintained, whereas maintenance on a gas-powered car is much more expensive. Okay, you have to get your oil changed, you have to, check your spark plugs, and there's just a lot of, basically you're containing an explosion in an internal combustion engine, and those things, have wear and tear on a car, so it's much more expensive to maintain. Gas-powered cars are less environmentally friendly, of course, and electric are more environmentally friendly. So that's just a kind of a case study in thinking about embodied energy, embodied carbon. The embodied carbon here is also much greater. So yes, there's a lot of carbon that is produced to make the car. If you can use uh, renewable resources to charge it, though, then that's a big though. If you can use renewable energy to charge your car, then it is much, much more environmentally friendly compared to a petrol vehicle, which is spewing out carbon dioxide. And essentially every car you see on the road is a global warming machine. Okay, so now we're going to talk about embodied carbon. So carbon is generated when producing a product, right? Like you have to understand what we mean by carbon here, right? There are lots of sources of carbon, and essentially, anything organic, like the name organic, has to do with the fact that it has carbon, nitrogen, oxygen, and hydrogen in its molecules, right? So, anything that is organic, that means anything that is alive or ever has been alive or is a building block of life is going to contain carbon. And carbon has a cycle. So carbon will get trapped in places. For instance, when you go and look at the rocks and the beaches around here, they've got trapped carbon in there. The rocks are made of something called calcium carbonate, which was laid down by ancient corals millions of years ago. So those are all there. You look at limestone. Limestone is calcium carbonate also, and it was laid down in warm seas where it simply precipitates out of the water, right? So there's a lot of trapped carbon in the earth, and one of those sources of trapped carbon is coal. It's basically fossil fuels, so coal, oil, and gas. Those things are trapped carbon, and for millions and millions of years, they basically stayed where they were. Now we come along, and what we're doing is we're taking this carbon that was trapped and essentially not part of the carbon cycle in on the surface of the earth, and we are releasing it into the atmosphere, right? And that's causing problems. That's what's causing climate change. So when we're talking about carbon, we're talking about organic material, right? So in here, he talks about how some of the best new building techniques will reduce carbon emissions. They're actually, by building this building, we actually reduce the amount of carbon that is released into the atmosphere. So it's kind of an interesting video. Make sure you watch it. So I'll pause and go ahead and watch that video. Okay. When we're talking about embodied carbon, we want to talk about also the gases that get released. So these are all, well, except for nitrous oxide, these are all carbon-based, well, and nitrous tetrafluoride, and I guess sulfur hexafluoride. Sorry, I guess there's some in here that are not carbon-based, but many of these are quite carbon-based. Okay, so carbon dioxide is considered a 1 on this GPW scale, and that stands for global warming potential. Okay, so what is the potential of any particular gas for causing global warming? Okay, so you can see that in carbon dioxide, it's considered a 1. Okay, now we don't know how long those things last, right? We don't know how long the carbon's going to be in the atmosphere. It's going to be in, even if we were to stop all carbon emissions by human beings today, it would take many, many hundreds, maybe thousands of years to return to equilibrium. Okay, methane is also a potent, and you should look in the text on the same. I don't know if it's on the same page or on one of the pages that's near this table. It shows you these how much these are in the atmosphere. Okay, and so the ones down towards the bottom, there's much less of them. Really, the two biggies are these guys right here. Okay, and then also water vapor, which is not on this list because we can't control that, but we can control how much of these things we pump into the atmosphere. So methane is basically if you had 1 kilogram of carbon, 1 kilogram of methane would be worth 25 to 28 kilograms of carbon in its effect on global warming, on its global warming potential. Okay, and as you go down the list here, yeah, this nitrous tetrafluoride, which I have no idea what it is, but like it's potent. That stuff gets into the atmosphere, it stays in for 500 years, and it's 1 kilogram of this stuff pumped into the atmosphere is worth basically 16,800 to 17,200 kilograms of carbon dioxide pumped into atmosphere. So it's quite a potent um, gas. Okay, and same with this sulfur hexafluoride. Look at this, in there for 3,200 years, and it's 23,000, almost 24,000 times more potent than carbon dioxide. So these would be things that we would definitely try to make sure we're not pumping out into the atmosphere. Last thing I want to talk about is carbon emissions by sector. So you can have a quick look at this. So, globally, when we're looking at greenhouse gas emissions, like where do we get the most, so when you're looking at electricity production, this is where we're getting a quarter of our carbon emissions. Okay, and down here we got agriculture, and you can see the chart. So um, that's this is important, and we would want to try to reduce these where we can. Transportation is 14% of the world's carbon emissions. If you could knock that down and change the amount of carbon emissions, that's going to have a big impact. And same with producing electricity. This is really the one that people are working on the hardest, where you've got the renewable sources of energy. These are the ones that are going to really have an impact on greenhouse gas emissions, as well as agriculture and these other things. But it all helps. This is the thing: little things help, because if everybody was to do the little things, then it adds up. Okay, it would have an exponential effect based on that. Okay, see you guys later. Thanks for watching.